We discussed about the Bode plot of basic factors. Basic factors as in simple pole of the order, let's say, 1 by s to the power p, where p is the type of the system. And we saw that the slope for this particular simple pole at origin. Okay, so this is nothing but simple pole at origin, because when you equate s to the power p to 0, you will get the root value at origin, right? So slope is found to be minus 20 into p decibel per decade. So if power is 1, slope is minus 20. If power is 2, slope is minus 20 into 2. All right. So similarly, we also looked at simple 0 at origin. And let's say the 0 order is s to the power m. Okay. So simple 0 at origin will give a slope of plus 20 into m decibel per decade, right? Where m is basically a multiplier. If you have m is equal to 1, slope is plus 20 decibel per decade. M is equal to 2, it is 20 into 2 decibel per decade, so on and so forth. All right. And we also looked at the angle contributions by the simple pole and simple 0. So simple pole gives angle phi as minus 90 degree. On the other hand, 0 being the numerator factor, and numerator factor is going to give you a positive angle, which is 90 degree. Okay. And we also saw constant gain k. So constant gain k basically gives slope is equal to 0 decibel per decade. So 0 decibel per decade means straight line parallel to the x-axis, and the angle part is 0 degree, right? So these three factors we discussed in the previous class, and I have given you a homework regarding first order pole and first order. Okay. Have a first order pole or first order 0. So let's say you have first order pole. Okay. First order pole as in let's say g of s into h of s is equal to 1 divided by 1 plus est. Okay. Where t is equal to time constant and omega c. Okay, in control systems, the reciprocal of t. Okay, I mean in reciprocal of t in normal terms, it is frequency, right? So let's consider angular frequency, and we'll give this suffix c also. That means omega c is called as corner frequency. Okay, a particular name is given for this particular frequency, that is corner frequency. So this is the corner frequency of this particular factor. So corner frequency is nothing but reciprocal of time constant. That's all. Okay. So you need this corner frequency in order to show the slope. In order to show the slope, you need to calculate the corner frequency, and corner frequency can be calculated simply by taking the reciprocal of the time constant. All right. And let us also replace s with j omega. So when we replace s with j omega, we will get the time constant form as 1 plus j omega into t. 1 plus j omega into t. All right. Fine. So that's our complex number. Now let us find out the magnitude. So next to write magnitude plot. Now in magnitude plot, what is that you should do? you should find out the magnitude of this particular complex number. All right. So how will you find out the magnitude of the complex number? So let's say magnitude m is equal to, in decimal I'm going to take 20 log to the base 10, and this is going to be mod of 1 plus under root 1 plus omega t square. So it is basically, let's say you have x plus iy. So mod becomes under root x square plus y square, same thing. So x being 1, so it remains 1, and y being omega t, so it is omega t the whole square. So it is omega t the whole square. Okay, this is what you get. Now what you can do is you can carry out the approximation. Okay, so approximation. So approximation is that, let's say for low omega values, for lower values of omega, this omega t, the product omega t, becomes very, very small for lower values of omega. So what happens? If let's say omega is 0.1, when you square 0.1, you will get 0.01. So this entire product becomes very, very small compared to unity. So you can write basically that implies 1 plus omega t the whole square approximately can be written as omega t the whole square. So with this approximation, you can write magnitude m is equal to 20 log to the base 10. And what do we have? Under root omega t the whole square, or it is simply 1 by omega t. Okay. So this is basically called as, you can write a comment, this is called as straight line approximation. So this is called as straight line approximation. Okay. So why are we doing this straight line approximation? Is to reduce the calculation burden, or else, for every discrete value of omega, you have to calculate. See, you substitute omega as 0.1, then 1, 10, 100, and you have to, start finding out the magnitude for every discrete value of, frequency. To avoid this, we go for the approximation. However, in MATLAB doesn't do approximation. So MATLAB basically gives, because it's a computer, right? It's a computing software. So computing software is very powerful. It can assume, infinite values of omega, let's say between the 2 decades, and it can give an exact plot. So if I were to compare the MATLAB plot, let's say MATLAB plot, I'm going to give you something like this. Okay, this is your MATLAB plot. On the other hand, okay, so this black one is MATLAB plot. So the approximation, what we are trying to use is straight line approximation. So straight line approximation basically gives kind of this. Okay, it comes here and then it moves straight. So this is what is called as straight line approximation. This is straight line. It's fine. You can see that small deviation will be there. Okay, so that's fine. Okay, now that we have got the magnitude as 20 log 1 by omega t, you can quickly verify, right? So what do you get? M is equal to, okay, let me use log of a by b formula, that is log a minus log b. So you will get 20 log to the base 10 unity minus 20 log to the base 10 omega t. So this is 0 dB, right? So 20 log 1 is 0 dB. So basically you will get m is equal to minus 20 log to the base 10 omega t. Now, if you look at the equation, you can clearly extract the slope from it. So this is your slope. And what is the slope value? Slope value is minus 20 decibel per decade. So basically, your first order pole gives a slope which is equal to minus 20 decibel per decade. Right. See. This is decibels, and log omega is basically your frequency scale, which is varying logarithmically, right? So magnitude is getting varied by a factor of minus 20. So a first order pole will give a slope of minus 20 decibel per decade. Now, let's say you have the power as, let's say, n. Let's say you were to have 1 divided by 1 plus st cube. So if at all cube is present, what happens is that the slope becomes minus 20 into n. So if the power of first order pole is n, then slope is equal to minus 20 into n decibel per decade. So square term will give you minus 40, cube term will give you minus 60 decibel per decade, so on and so forth. Once again, the one thing is very clear over here is that whenever poles comes into picture, you will get a negative slope. And whenever 0 comes into picture, you should get a positive slope. So whenever you get a first order pole, you can simply draw a straight line having a slope of minus 20 decibel per decade. So that's the takeaway. All right. Okay. Let us consider the phase plot. Phase plot. Okay. So quickly let me write g of j omega into h of j omega. That is 1 divided by 1 plus j omega t. All right. So angle phi. Angle phi is what? Angle of g of j omega into h of j omega is equal to, okay, so numerator angle, so tan inverse of 0 by 1, so that's actually 0. So numerator angle, okay, so let's say this is phi 1 and this is phi 2. So phi 1 is 0, right? And what is phi 2? Phi 2 is tan inverse of y by x, so it is omega t divided by 1, which is basically omega t. So numerator angle is 0 degree and denominator angle is tan inverse of omega t. So when you find out the net angle, what do you get? Summation numerator angles minus summation denominator angles. So n is equal to numerator angles and phi d is equal to denominator angles. So what do we get? The net angle as? Net angle, we will get it as minus tan inverse of omega t. So as you can clearly observe that the first order pole, the angle contributed by the first order pole is frequency dependent. So when you vary omega, the angle varies. All right. So don't have to plot a separate graph for it. You can always say that as we start varying the value of omega, phi value starts varying. Okay, so that is your phase plot. Okay, so noticeable, information in this particular discussion is that your first order pole gives negative angle. And the first order pole also gives negative slope. All right. So that is the main thing. Now, in a similar way, you can evaluate the slope contribution and the angle contribution of the first order 0. Let's say you have first order 0. Let's say g of s into h of s is equal to, let's say, 1 plus st, right? So this is your 0. So this is called as first order 0. So magnitude n, okay, it becomes directly, let me write, 20 log to the base 10 mod of under root 1 plus omega t the whole square. And for lower omega values, you can write omega t the whole square is very small to unity. Hence, 1 plus omega t the whole square can be approximately written as omega t the whole square. So therefore, magnitude m becomes 20 log 20 log omega t, right? Because the factor is in the numerator. So it is 20 log into omega t. Now you can clearly observe that your slope, okay, this is y is equal to mx, right? Plus c. Okay, anyhow, the c factor is 0 over here. You can clearly observe that x is your log scale, that is frequency, okay, whereas logarithmically, and your y is magnitude expressed in decimal. And what is factor m? Factor m is 20. And what is the sign? Sign is positive. So you can say that your first order 0 gives positive slope. Right, that's all you need to know in Bode plot. Pole gives negative slope, 0 gives positive slope. Pole gives negative angle, 0 gives positive angle. That's all you have to know in Bode plots. Okay, so that's your. Now, if I were to take, let's say, the first order pole power as, say, some n, then your slope would have been plus 20 into n decibel per second. That's all. So n becomes the multiplication factor. 20 into 2, 20 into 3, 20 into 4, so on and so forth. So that's about the magnitude plot of first order 0. And phase plot, pretty easy, right? So phi is equal to, as I said, numerator angles minus summation of denominator angles. So you can write phi is equal to, what do we have basically? We have phi is equal to tan inverse of omega t, that's all. So we don't have any factors in the denominator, so your ID is 0. So your angle phi is simply tan inverse of omega t. As you can clearly observe that angle phi is now having positive sign. So first order 0 gives positive, and trust me, this is all what you need to understand Bode plot. And this can be, carried forward for a quadratic pole as well as quadratic 0. So what I will do, I'll not do any, give any proof for quadratic pole or quadratic 0. Okay, because you can, I'll provide in the notes. Okay, you can go through. Let me just deal it, qualitatively. Let's say I take a quadratic pole. Quadratic pole. What do you mean by quadratic pole? Quadratic pole as in g of s into h of s is equal to 1 divided by, let's say something of this kind you have, x squared plus 2 zeta omega ns plus omega n squared. So whenever you deal with quadratic pole, the corner frequency is nothing but omega n. What is omega n? Natural frequency of oscillation. Natural frequency of oscillation. Natural frequency of oscillation. Okay, so this is one thing. Okay, this is how you calculate the corner frequency for a quadratic factor. For a simple pole or 0, it is simply the reciprocal of the time constant. Here, you cannot accept the time constant, hence you can directly take the natural frequency as the corner frequency. So that is one thing. Second thing is the slope. Okay. So what is the highest power of S? It is 2. And what is it? It's a pole. So pole always gives negative slope, right? We have already seen. So why I have written negative sign? It is I have written because the past experience has revealed me that poles are going to give me the negative slopes. So negative sign I put. Since power is 2, it is always 20 into 2. So it is 40. So your quadratic factor gives plus or minus 40 slope. Plus for 0 and minus for pole. So slope is minus 40 decibel per decade. Minus 40 decibel per decade. All right. And angle phi. Okay. You can write down. So angle phi is angle of g of j omega into h of j omega. You don't have to break your head for angle. Okay. So you can always substitute S as j omega, and you can separate out the real and imaginary parts. Once you have real and imaginary parts, you can just apply the trigonometry relation, right? Tan inverse of imaginary part by real part. Okay, let's do that. So let's substitute S is equal to j omega. So what do I get? So I get g of j omega into h of j omega is equal to 1 divided by, this is j omega the whole square. So it becomes minus omega square, right? Because j square is negative 1. And this becomes plus 2 zeta omega ns. So this is j 2 zeta omega n into omega, right? And this becomes omega n square. Omega n square. Okay, remember one thing, omega n is constant. It is constant for particular system, right? Because that's the natural frequency of oscillations, right? And what is this omega? This omega is variable. This omega is variable. Variable as in that's the source frequency, the input signal frequency, which you when vary, the magnitude and the phase angle is going to vary. So once you have this complex number, you can separate out the real and imaginary part, something like this. So I have this being my imaginary part and this being my real part, right? So I can write down omega n square plus omega square minus omega square plus j 2 zeta omega n into omega. All right. Or you can write down phi is equal to tan inverse of, obviously minus, because the factor is coming in the denominator and the numerator angle is 0 degrees. So when you take out the net angle, it is numerator angle minus denominator angle. So minus tan inverse of imaginary part. What is it? 2 zeta omega n into omega. 2 zeta omega n into omega divided by the real part. What is it? Omega n square minus omega square. Okay. So what you have to do is you have to just substitute omega value and you can find out the phi value. Okay. So that is your phase angle plot. Okay. So similar expression can also be written for a quadratic 0. Okay. So wherever you have negative sign, you replace it with positive sign. Okay. I think you will be able to comprehend the situation. So quadratic 0, you can handle it with just the positive sign. So slope, you take it as plus 40 decibel per decade, and angle, when you write down, you write it as tan inverse of, plus sign you have to add. That's all. Fine. So that's it from the basic factors side. Okay. So let's jump into a problem. Okay. First problem, let us take. I hope you have the similar graphs with you. Write down. what I'll do, let me start with a simple problem. Okay, we'll just find out gain crossover frequency, phase crossover frequency, gain margin, and phase margin. Followed by, the tougher part. Okay, for a given gain margin, what should be the value of K? Or for a given phase margin, what should be the value of K? Okay, so that can be dealt in the second part. All right, right on. For the given system, obtain the Bode plot and determine omega GC, omega PC, gain margin, and phase margin. So you need to determine omega GC, omega PC, phase margin, and gain margin. Okay. So solution. Step 1, time constant form. Step 1 is time constant form. Time constant. Okay. So first let us derive the time constant form. So how do we do it? G of s into h of s is equal to dt. Okay, time constant form and put k equal to 1. So that means to say we will set the value of k as 1. And the remaining information can be extracted from the Bode plot. Okay, sometimes they will say take k is equal to 10 or say k is equal to 15. So if they specifically mention, you can take the value. If they haven't mentioned, for example, in this problem, they haven't mentioned the value of k. So to start drawing Bode, what you can do is you can put the value of k as 1. All right. So when you substitute, you will get numerator factor as 18. And to convert it to time constant form, what you have to do is you have to, take out these numbers outside the bracket, pull them out. So what do you get? When you, this is 2 into, I'll take even 20 outside, and then the whole at origin into, okay, this I have taken out. So what do I get? 1 plus s by 2. What is s by 2? It is 0.5 s. Okay. And then 1 plus s by 20. So s by 20 is 0.05 s. 0.5 s. And you can simplify, right? So 2 into 20 is 40. So 80 by 40 is. So basically, you get g of s into h of s is equal to 2 divided by s into 1 plus 0.5 s into 1 plus 0.05 s. So this is your time constant form. Then step 2, probably you can substitute s is equal to j omega. So when you substitute s is equal to j omega, you will get your open loop transfer function in frequency domain, right? Because omega is complex frequency. So 2 divided by j omega 1 plus j 0.5 omega into 1 plus j 0.05 omega. All right, so that's your time constant form expressed in frequency domain. So these two are major steps. Let's say if this problem is asked for 10 marks, this particular step will get you 2 marks. 2 marks. All right, fine. Next, you write step 3. Once you have the transfer function in hand, you can go for step 3, which is magnitude plot, and then step 4, which is phase plot. That's all. 4 steps. Step 3 is magnitude plot. Magnitude plot. All right. So magnitude plot, you can do something like this. Okay, first let me write down the transfer function g of j omega into h of j omega is 2 divided by j omega into 1 plus 0.5 j omega into 1 plus 0.05. All right. So in order to draw magnitude plot, first and foremost thing is that you must write down the corner frequencies, right? Because you have to arrange the factors in the ascending order of corner frequency. All right. So first let us find out the corner frequency of this. This is not in time constant form, right? Time constant form means 1 plus j omega t form. So this is not in time constant form. So there's no corner frequency. You can just put dash. Okay, and that will be the starting frequency. Okay. So because this factor is found at origin, so origin is nothing but your starting point for your Bode. Right. And what is the corner frequency of this? Say omega c1. So omega c1 is 1 by 0.5, which is 2 radian per second. Basically, this only you are going to get. Okay. Similarly, this you can take it as omega c2, which is 1 by 0.5, and that will give you 20 radian per second. Okay. So this is what you are supposed to do. Find out the corner frequency. Okay. Once you find the corner frequency, you can create the magnitude table. So over here, I want your undivided attention. If you don't pay attention, you will not understand my method, because books will have different methods. This is my own method, which I'm pretty comfortable in drawing the Bode. All right. So please pay attention. So what we will do, first we will write factor, and then corner frequency omega. Omega c stands for corner frequency. Okay. And then let me write individual slope. Okay. And then let me write the net slope. Right. What is net slope? Net slope is previous slope minus current slope. So previous slope minus current slope. Now, what do you mean by factors? You remember, I was saying that a typical open loop transfer function can have different factors: simple pole, simple zero, first order pole, quadratic zero, etc., etc. So those are nothing but factors. So what you have to do is you have to identify the factors in this particular transfer function. So as you can clearly observe that there are no zeros, right? There are no s terms in the numerator. So what you have is the poles. All right. Now you have to consider these poles in a systematic manner. Systematic manner in the sense, the factor which is having the least frequency should be tabulated first, followed by the next highest frequency, so on and so forth. So the first factor is nothing but the pole at origin. So in the numerator you have 2, right? So what I will do, I will club this 2 with the pole at origin. And this will be my first factor. So under factor, what I will do, I will write 2 by j omega. 2 by j omega. Okay. And what is the corner frequency? Actually, corner frequency is 0, right? Because at origin, omega value is 0. But we have a problem here. What are we finding out? We are finding out magnitude. Now, while finding out the magnitude, especially decimal magnitude, when we take 20 log omega, and if we substitute omega equal to 0, we get infinite dB. So what happens is that you will not be able to evaluate the gain at origin. So to come out of this, infinite decibel problem, what we can do is, instead of 0 radian per second, you consider a frequency which is very close to 0. Let's say 0.1. Okay, and omega c is expressed in radian per second. I hope you understood the point, because I cannot take omega equal to 0, because if I take, I'll get infinite gain, which is strictly no condition, right? Because it cannot handle DC signal. That's the reason, instead of origin, I'm considering a frequency which is very close to 0. Say, for example, 0.1. You can even consider 0.01, doesn't matter. All right, fine. Now, coming back to individual slope. So, what is the slope contribution given by a simple pole at origin? What is the power of this? The power is 1. So, a simple pole at origin gives minus 20 decibel per decade. Right? Minus 20 decibel per decade. So, the net slope becomes previous slope minus current slope. Now, there is no previous history, right? So, previous slope basically 0. So this is net slope, right? Net means total. Net means total. So previous plus current. So previous is 0 and current is minus 20. So net slope is minus 20 decibel per decade. So you have to draw a straight line with a slope of minus 20 decibel per decade. How to draw? I will tell you later. Okay, but since you have considered the starting frequency as 0.1, you have to find from what point the magnitude plot starts. So in order to find the starting point on y-axis, so you can write over here, to find starting point on y-axis, right? Because you can draw minus 20 decibel per decade slope, but at what point you should start drawing? So that can be found only by finding out the point value on y. So that's pretty simple. What you can do is you find this 20 log to the base 10. Find out the mod of this function, that is 2 by j omega. What is it? It is basically 2 by omega. So 20 log 10, 2 by omega. Okay, and what have you taken omega as? You have taken omega as 0.1. So basically, you are trying to evaluate the magnitude m at the starting frequency. So starting frequency you have assumed as 0.1. If at all you were to take this omega as 0, you would have got the magnitude as infinite. So how do you locate the infinite point? It is not possible, right? So that's the reason a frequency very close to 0 we have considered. So quickly you can find out. So 20 log 2 minus 20 log omega. So what is omega? Omega is 0.1. So 20 log 2 minus 20 log 0.1 will give you m is equal to 26 dB. So 26 dB is your starting point. So what you have to do is you have to mark 26 dB on y-axis, and from 26 dB onwards you have to draw a straight line with a slope of minus 20 decibel per decade. All right. So I'll write and y at omega equal to 0.1 instead of y. I will write m. Okay, because magnitude, right? So m at omega equal to 0.1 is 26 dB. Yeah, so that's my first factor. So this y needs to be, sorry, m needs to be calculated only once. Okay, because that's the starting point. Once that is done, you can start listing out the factors in the ascending order. So least comes first. So 0.1 you have written. Next is 2 radian per second. Okay. Followed by what do you have? 20 radian per second. Okay, put the unit here itself, radian per second. So what is that factor? It is 1 divided by 1 plus j 0.5 omega. So 1 divided by 1 plus j 0.5 omega. And the factor corresponding to 20 radian per second is again first order pole, which is also 1 plus j 0.05 omega. Alright, so fine, we have listed out the factors in the ascending order of corner frequency. So what is the individual slope given by a first order pole? It is minus 20 decibel per decade. And then this factor again, it's a first order pole, it gives minus 20 decibel per decade. From where we are writing all this? From the previous lesson, right? We have already seen. Fine. Now you calculate the net slope. So over here, what will be the net slope? Previous minus current, right? So how much was the previous value? Previous value is minus 20, right? And plus the current value. Current is also minus 20. So minus becomes minus 40 decibel per decade. So what is the meaning? So from omega c equal to 0.1 to 2 radian per second, the slope remains minus 20 decibel per decade. So from 2 radians per second onwards, a simple pole comes into picture. So that will introduce an additional slope of minus 20 decibel per decade, due to which the total slope becomes minus 40 decibel per decade. So from 2 radian per second onwards, the net slope becomes minus 40 decibel per decade till the next corner frequency. So minus 40 decibel per decade, okay, is the slope. Okay, so I'll write to be drawn from 2 radian per second to 20 radian per second. All right. So between 2 frequency, the poles or zeros, start to appear in your system, right? Now let us look at the third factor. So the third factor gives an individual slope of minus 20 decibel per decade, due to which the net slope becomes, okay, what is the previous slope? The previous slope was minus 40, right? But the current slope is minus 20. So the net slope becomes minus 60 decibel per decade. So what is the meaning of this minus 60 decibel per decade? So minus 60 decibel per decade simply tells you that from 20 radian per second onwards, the magnitude plot moves with a slope of minus 60 decibel per decade. Till where? Is there any defining frequency? There is no defining frequency. So from 20 radian per second to infinity. Just goes on. That magnitude plot keeps on moving with a slope of minus 60 decibel per decade. So that's your magnitude table. So if you do this magnitude table, you will get about 3 marks. So 2 plus 3, 5 marks. So out of 10, already you have scored 5 marks. And 3 you will get it for, sorry, 2 marks you will get it for your phase plot, and 3 marks for the final Bode plot. Okay. I hope this is clear. So this is your magnitude table. Just keep on adding these slopes from the previous factors. Okay. Step 4. Phase plot. So for phase plot, what we need phi. So phi is equal to, sorry, angle of g of j omega. Phi is equal to angle of g of j omega into h of j omega. So that is equal to, we can say 2 plus j0 in the numerator divided by angle of j omega, angle of 1 plus j 0.5 omega, angle of 1 plus j 0.05 omega. Right. So this is your system angle. So we can put it into a nice equation basically. So phi is equal to, okay. So let me use different color pen. So what is the angle of this? 0 by 2. So that's 0 degree, right? So angle contribution given by factor K is 0 degree. We have already seen, right? So this is 0 degree. And what about this? This gives 90 degree, right? Tan inverse of, why 90 degree? Because tan inverse of imaginary factor is omega, and there is no real factor. Omega by 0 is infinity. Tan inverse of infinity is 90 degree. So this factor gives 90 degree. On the other hand, this factor gives tan inverse of 0.5 omega as the angle. And the last factor gives the angle as tan inverse of 0.05 omega. So these are the angles given by the system. So now you can put it into a single equation. So numerator angle is 0. I don't have to write it, right? Minus the denominator angles. So minus, right? Because all these angles, when it goes to the numerator, everything becomes negative. So minus 90 degree, minus tan inverse of 0.5 omega, all right? And what do we have? Minus tan inverse of 0.05 omega. So this is my angle equation. After this, what you do is you create a simple table, two-dimensional, right? X variable and Y variable. Your X variable going to be the frequency and Y variable going to be the phase angle phi. So start allocating different frequencies and start finding out the values. So for this, what you can do is in your calculation, you can keep this particular equation in equation mode, right? So you go to equation mode and recreate this type of equation with a variable. Okay, so probably you can keep the variable as a, and you can keep on varying the value of a, and you can get the value of phi. Okay, so some random values of frequency you take. Okay, when you take the frequencies, make sure that you take at least 10 points. Okay, so that your curve becomes smooth. If you take some 3-4 points, what will happen is you'll get a jagged curve, which is not good actually. Okay, so some 10 points you take, say 0.1 and 2, 4, 6, 10. Okay, and let me continue here. And 5. Okay, I already calculated, so you can do it later. You can cross-check the answers. If you have any discrepancy, you just let me know. So this is say 1000. That's fine. Okay, so 0.1, I get about minus 93.14 degree, and this is minus 140.7. Okay, so this is expressed in degrees. Okay, and this is radian per second. All right, I have already told, right? This is radian per second. So at 4, you get minus 64.7, and at 6, minus 178.26, and at 10, you will get minus 195.29. This is minus 209, minus 219, minus 257. Don't worry, this I've already calculated the value. This is minus 268.74. All right. So this is what you get when you substitute the value of omega into this particular equation. Okay. Now, one tip I will give you. The very important tip is that whenever you draw phase plot, you will have to populate the frequencies near to minus 180 degree crossover, because when the phase plot cuts minus 180 degree line, you will get something known as phase crossover frequency. In order to accurately determine the phase crossover frequency, probably you can populate. See, where is it getting crossed? Minus 180 degree line. See, at 4 it is minus 164 degree, and at 6 it is becoming minus 178 degree, and at 10 it became minus 195. So between 6 and 10 you have your minus 180 degree line crossover. So probably what you can do is you can populate this particular region, so that you will be able to accurately determine the phase crossover frequency. So what I've done, I've directly jumped from 6 to 10, right? So probably you can take, say, 7, 8, 9. Some 3 ratings you have to introduce. Even if you don't introduce, nothing will happen. But pro tip, I would say. All right. So say pro tip. Populate the frequency near minus 180 degree angle. All right. So that's my phase plot. So this will again get me about 2 marks. 2 marks. So total out of 10, we have scored already 7 marks. And the remaining 3 marks are reserved for the diagram. All right. The plot. Fine. So let's do the Bode. I hope you have the semi-log graph sheet with you. So whoever is, planning to pursue their higher studies, whether India or abroad, in let's say analog electronics, VLSI, embedded systems, for that matter, even power electronics, signal processing circuits, you should have the thorough knowledge of Bode plots. Don't think that this hand calculation is outdated. Yeah, of course, we don't do it in real world, but we take the MATLAB results. But you need to understand the plot, right? A bare graph cannot convey the meaning of or the conclusion of the design. So you need to understand this Bode plot very, very clearly, because that's like a foundation for your future. All right. Let's consider the Bode now. Okay, semi-log graph. So this is what I've done. Let me show you. This is how I have plot. All right. So this is my Bode diagram. So what I have done is, first I have taken magnitude plot. So on top you take magnitude plot, and at the bottom you take the phase plot. All right. So your x-axis will be the single axis. That means to say you are going to take frequency along x-axis. On the other hand, your y-axis is split into 2 axes, right? One axis you have dedicated for your magnitude plot, where you express the variables in decibels. And the second y-axis you will use to plot the phase angle variation with respect to frequency. So for magnitude plot, y-axis is decibels, and for phase plot, the y-axis will be degrees. All right. Fine. So that's how you have to do it. Fine. Okay, so let me take, let's say, this for your top half for magnitude, and let's say bottom half, let me use it for phase plot. Okay, so these are my decades, all right? So these are my decade frequencies. Not done. Okay. 1050. It's not at 1050, it's at 1150. And second one, this is second hour 1050. Okay, sorry. Okay, all right. So this is my decade, all right. So what I've done is, let's say this is my, here I write, okay. The starting frequency, okay. This is your omega, basically log omega, you can say. Okay, this is also your omega, all right. And then y-axis, let's draw. Okay, so similarly for phase angle. Okay, so for magnitude plot, what I will do is, decibels, all right, and this is degrees, decibels and degrees. So let's say this is plus 20, plus 40, plus 60, and this is your 0 dB, all right. So this is your 0 dB line, and anything below 0 dB will have the negative value, minus 20 and minus 40, all right, dB. Again, I have already defined the y-axis, and in the phase plot, you don't have 0 degree line, right? You have plus or minus 180 degree line. Why plus or minus 180 degree? Because it is derived from the angle condition, right? And 0 dB is the magnitude condition. Mod of g of s into h of s is equal to 1. Or in decibel system, 20 log 1 is 0 dB. All right, so this will be your minus 180 degree line. So anything above minus 180 degree is considered as increasing angle sense, and anything below minus 180 degree is considered as decreasing angle sense. So minus 180, and this is minus 150, minus 120, and minus 90, so on and so forth. So this is minus 210, minus 240, minus 270, so on and so forth. So what I've done is, I've taken one unit as 30 degree for phase angle plot, and one unit as 20 dB for magnitude plot. Okay, and these are all decades. Okay, these are all decades. Okay, now let me do the frequency scale marking. All right, so I don't want to populate the scale over here, because I have to capture omega GC, omega PC, etc., etc. So what I will do, I will write it at the bottom, right? So this is my starting frequency. Can I take 0 radian per second as starting frequency? No, I cannot take. So 0.1 is my starting frequency. The next decade going to be 0.1 into 10. So it is 1 radian per second. 1 into 10, 10 radian per second. Then you have 100 radian per second, 1000 radian per second, 10,000 radian per second, so on. So that's how you select, or rather you describe the omega scale. Let me just quickly repeat. 0.1 is my starting frequency. I'll multiply with 10. I get 1 into 10, 10 into 10, 100, 1000, 10,000. All right? Fine. And in between 0.1 and unity, you will have unequal partitions, okay? Because that's the semi-log graph nature, which I'm not able to draw it here, okay? Because it becomes too complicated for me to draw. So you can see here, right? So this is one decade. You can see that you have a non-uniform scale between 0.1 and this first unit. You will have kind of bigger scale, and the scale goes on shrinking. So what you have to do is, if this is your first frequency, this frequency is nothing but, okay, here they have written 2, then 3, 4, 5, 6, 7, so on and so forth. So there will be 10 partitions within a decade. All right. So this is number 2, right? So this frequency is 2 into starting frequency, that is 0.2 radian per second. So this is how we read. Let's say you want to check the frequency over here. All what you have to do is you have to identify the number. Let's say number 7. So 7 into the starting frequency will give you 0.7 radian per second. So that's how we read the semi-log scale. Okay, fine. Let's go with the magnitude plot. So what I want you to do is, I want you to look at the table which we created earlier, right? The magnitude table. So this table we had created earlier, right? Yeah. Just look at the table. Okay. So starting frequency is 0.1. And what is the net slope? Net slope is minus 20 decibel per decade. Now the problem is, or the question is, how will you draw minus 20 or minus 40 decibel per decade lines? To draw, these lines, negative slope means downgoing line. Okay. So if this is my 1 decade. So if I connect 20 dB to the first decade, okay, thin lines are reduced. What do I get? My gain is 20 over here, and it is reducing. And finally, at this decade, what is happening? It is becoming 0. So that is called as negative slope, because the magnitude keeps on falling. Okay, so that is negative slope. So what is slope? Y by x. What is y? Y is 20. And what is x? X is a decade. So 20 decibel divided by decade. So that is your minus 20 decibel per decade. Why minus 20? Because the magnitude is decreasing. Okay, since I don't want to write minus 20, minus 40 because it consumes a lot of space. What I will write? Minus 1. Minus 1 means minus 20. Minus 2 means minus 40. Okay. Now let's say I want to draw minus 40 decibel per decade slope. So what will I do? Just connect this 40 to the first decade. Similarly, you connect 60 to the first decade. So this gives you minus 20 decibel per decade. This gives you minus 40 decibel per decade. And this gives you minus 60 decibel per decade. So we don't have to worry about positive decibel per decade because we don't have any factors. Now, let's say if you have any zeros in the system, then how you would have handled that particular case. So if at all you have zeros in the system, you will get positive slope, isn't it? So what you have to do is, from negative 20, you connect to the decade. Similarly, from negative 40, you connect it to the decade. Now what is happening? The slope is increasing, right? The slope is increasing. Initially it is minus 20, and then finally it becomes 0. So that is called as, the increasing trend. So for zeros, probably you can take these as the reference slope. So this I'll take plus 1 and this I'll take plus 2. So this is how we draw the reference slope lines, which will help you in drawing the magnitude plot. All right. I hope we are good till now. Okay. Now coming back to magnitude plot, we see that the magnitude is 26 decibel at 0.1. So what you have to do is you have to mark the initial magnitude at 0.1. So that is 26 decibel. Let's say somewhere here is your 26 decibel. And right here, 26 decibel. So from 26 decibel, the magnitude plot starts. Okay, with a slope of minus 20 decibel per decade. Till where you have to draw this minus 20 decibel per decade line? Till the next corner frequency, which is at 2 radian per second. So what you have to do is you have to first identify 2 radian per second. Okay, so this is 1, right? So 2 radian per second will be, okay, this is 1, right? This is 1. So 2 radian per second will be somewhere over here. Just put a small mark. And, similarly here you write it's 2 radian per second. Okay, fine. Let's do that. So watch carefully. Keep your scale. Okay. Keep your scale on 26 dB. All right. And what is the reference slope you want? You want minus 20 decibel per decade slope, right? What you have to do is first you keep the scale at the reference slope. You want to draw a minus 20 decibel per decade line. So keep the scale at minus 20 decibel per decade reference line. All right. Then what you do, you shift it upwards. Where you have to shift? You have to shift to 26 decibel point. And then you draw a straight line till 2 radian per second. 2 radian per second. Now, if at all you have drawn properly, minus 1 line will be parallel to the line which you have drawn from 26 dB, right? So that is the reason we draw the reference slope lines. So reference slope lines will help us in drawing the magnitude plot. Okay, that is one trick. Another trick is just measure this distance from 20 dB. How many divisions it will take to reach 26 dB. So measure this distance and at 2 radian per second, place that distance and just connect the 2 points. It is up to you. Or how you draw the vector diagram, right? You have to draw a parallelogram. So parallelogram, in order to draw, what you do, you draw a parallel line from the reference line. Same thing we have drawn. All right. So we'll have to stop the line at 2 radian per second, right? So at 2 radian per second, what is happening? The first order pole comes into picture. And what is the nature of first order pole? 1 divided by 1 plus j 0.5 omega. So at 2 radian per second, the net slope becomes minus 40 decibel per decade. So from 2 radian per second till the next corner frequency, which is 20 radian per second, the straight line will have a slope of minus 40 decibel per decade. So to draw this, what you have to do is you have to identify 20 radian per second. Okay, so let's say this is your 20 radian per second. And here is your 20 radian per second. Okay, this is your 20 radian per second. Write it here, 20 radian per second. So minus 40 decibel per decade. So minus 40 means I have to use -2 decibel per decade reference line. All right. Then I have to draw. So it is a little difficult. So what I will do, I'll start from here. This is my -40. So it goes like this. Okay. Yeah. Very clear. So this I will write -20 decibel per decade. This I'll write -40 decibel per decade. So this point is 20 radian per second. Now, at the 20 radian per second, what do we have? At the 20 radian per second, we have a first order pole, right? Which is of the order 1 plus 1 divided by 1 plus j 0.05. And due to which the net slope becomes -60 decibel per decade. So what you have to do is you have to draw the reference line. So pretty difficult, right, to slide here. So what you can do, you can just draw an extension line, and then you can erase. Okay. So this is your -60 decibel line, decade line. So what I will do, I will take this as the line, and I'll slide it up so that the two lines are parallel to each other. And I will continue. So this will go to infinity, and the slope is -60 decibel per decade. All right. So this is what I've done. What I've done, I've just extended this -60 decibel per decade reference line, and then I just shifted my scale upwards so that this line is parallel to the reference line. Okay. Once the line is drawn, my purpose is served. So I will delete out the reference line. So that completes my magnitude plot. Right. Now what is happening? Your magnitude plot is cutting 0 dB line at this value. So this value is called as omega GC, which is called as gain crossover frequency. If you were to draw this graph very, very carefully, this gain crossover frequency, you will get it very close to 2 radian per second. Okay. I did not draw it with respect to graph. So yeah, 2 radian is here, which is very close to 2 radian per second. Okay, you can check, you can draw it in a graph sheet and you can check. So gain crossover frequency, I'll get it as 2 radian per second. Fine. This is my magnitude plot. Okay, here I'll write magnitude plot. Magnitude plot. And over here, I will have my phase plot. Phase plot, pretty easy. It's just like drawing a graph, right? Magnitude plot is little challenging. That means to say, not difficult. You'll have to spend some time there. Okay. So phase plot, let us draw. So at 0.1 radian per second, the angle is -93. You can refer the phase chart. So -93 is somewhere here. And then at 2, it is -140. So 2 is here. And -140 is somewhere here. Okay, and then at 4, -164. So 4 is somewhere here. -164 is somewhere here. And then at 6, it is -178. Somewhere here. Okay. And at 10, it is -195. So 10 is here. 195 will be somewhere here. 15, it's 210, approximately 210. 15 is somewhere here. then 20 to 20. At 100, it is 258. Here. And at 1000, it is 268. 1000 is here. It's 268. Yeah, that's all. So these are the points. Okay. Now what you do, you join these points with a smooth curve. Okay, you should be little artistic here. Don't do, that robotic graph. Okay, little. It shouldn't be a jagged line. It should be a curve. Right? We can start with a say pin connecting. Okay, something like this. You can draw. Something like this here. Okay, so this is your phase plot. This will go to. What is happening? Somewhere here, right? Your graph is cutting minus 180 degree time. So that is called as omega BC. So omega GC, you will get it as 2 radian per second. You have already pointed out. And omega PC, it is very close to 10. So somewhere about 7 or 8 you will get. Okay, if you accurately determine, yeah, you will get it as 6.6. Okay, so omega PC, you will get it as 6.6 radian per second. Stability you can tell by looking into omega GC and omega PC, as omega GC is greater than omega PC. System is stable. And you can find out the gain margin. Okay. So how will you find gain margin? To find gain margin, what you have to do is from omega PC, you have to draw a straight line vertically upwards such that it cuts your magnitude plot. Okay. So you have to draw a straight line from omega PC vertically upward such that it cuts your magnitude plot. And this distance, okay, let's say this is A, and let's say this point is A dash, A and A dash. So gain margin is nothing but length A dash. So what you have to do is you have to measure the length and multiply with scale. Okay, scale factor you know, right? Y-axis, 1 unit is 20 dB. So that is your gain margin. And if gain margin is found below 0 decibel line, we say it is a positive gain margin, right? So for this particular system, you will get the gain margin as 20 decibel. 20 decibel plus 20 decibel. Why? Because it is found below the 0 dB line. So what is the meaning? The meaning is that this particular system is having a provision to add additional 20 dBs of gain in order to bring the system on the verge of instability. So you can add up to 20 decibels. So addition is considered as positive, sense. Hence it is given with 20 decibels. Fine. So that's your gain margin. Next, you will have to find the phase margin. Reverse procedure for phase margin. For phase margin, what will you do? Identify the gain crossover frequency. That's here. And then draw a line, this time vertically downwards. So, what is happening? The line is cutting your phase plot at 2 distinct points, right? Let those points be, say, P and Q. So length PQ gives the phase margin. So for phase margin, you measure the distance PQ and multiply with scale. So when you multiply with scale, you will get the phase margin. So it looks slightly above 30 degree, right? Because if you see till here it is 30, slightly above 30 degree, 39 degree it is coming. So phase margin is 39 degrees. And the phase margin, right? The phase margin, this is your phase margin. So phase margin. So phase margin, where it is getting located? It is getting located in the increasing angle side, right? So see minus 180, minus 150, minus 120. So angles are increasing over here. So phase margin is found in the increasing angle trend, hence it is taken as plus. If your phase margin were to be found on the region which is below minus 180 degree line, you would have taken that particular phase margin as negative. So in this particular problem, gain margin is 20 decibels and phase margin is plus 39 degrees. So gain margin is positive, phase margin is positive, hence the system is stable. Okay. This is possible only if omega GC is greater than omega PC. So this particular system is said to be stable system. All right. So that is the first part. Okay. So what I will do, I cannot do the plot again and again. I'll just add some extension to this. Let me click an image of this. So that same thing I can share it in the class group as well. Okay. So this is your first part of the question, right? You omega GC, omega PC, gain margin and phase margin, and you are supposed to comment on this stability. Okay. So that's the 10 mark question. Sometimes the question remains the same. Instead of asking you to find out the gain margin and phase margin, they may ask something like this. Okay. Write down the second part of the question. Find K such that gain margin is 10 dB and phase margin is 50 dB. So what you have to do is you need to find K for a gain margin of 10 dB and phase margin of 50 degrees. So what is that value of K that can give you a gain margin of 10 dB and phase margin of 50 degrees? All right. So this is a separate question, nothing to do with the first question. Okay. Now, in this particular question, you need to find K to get a gain margin of 10 dB and to get a phase margin of 50 dB. Okay. So first what we will do, first we will consider the first case, that is gain margin of 10 dB. So you have to look at the sign of, so what is it? It is plus 10 dB. So what you have to do is you have to locate plus 10 dB gain margin in your magnitude plot. So positive gain margin is found below 0 dB line. So what you have to do is you have to mark plus 10 dB. So this is minus 20, right? So exactly half. So probably, okay, this itself is 20 dB, right? You have got, so exactly half you have to take, all right? So half is somewhere here. So you have to draw one reference line. Okay, let me use red color line. Okay. And let me write here 10 dB gain margin. 10 dB gain margin. Okay. Given in detail in notes. Okay. So first step is to mark the 10 dB line. And why did you get 10 dB? Because it is given so. The next step is to locate the phase crossover frequency. So where's the phase crossover frequency? It is omega pc, it is here. So what you have to do is, in next step, draw a straight line vertically upwards, which is already drawn, right? Now, draw a straight line omega pc such that it cuts the 10 dB line. So the 10 dB line is getting cut somewhere over here. Let me take that point as point B. Point B. All right. Now, I hope you are located point B, that is somewhere over here. Now, you see here, gain margin is calculated at phase crossover frequency, correct? So phase crossover frequency is here. But at this phase crossover frequency, the system gain margin is found to be A dash, which is 20 dB. But you have been asked to find the value of K to get a gain margin of 10 dB. But 10 dB is lying here. And your actual system is giving you a gain margin of 20 dB. So what is that you should do in order to get 10 dB of gain margin? Your entire magnitude plot should be shifted up, right? Your entire magnitude plot should be shifted up so that this A dash coincides with B, right? So what you have to do is plot should be shifted up by, okay, what is the margin? The margin is length A dash. Because if this point A dash comes on B, then the gain margin becomes 10 dB. So that is the idea. So basically, this can be done by varying the value of K. So you will have to first measure length A dash B. Okay. So length A dash B, you will get it as ten dB. Okay. So this you will get it as 10 dB. So the plot should be shifted up by 10 dB, you are saying. This can be done by incorporating K value. So 20 log K is equal to 10 dB. So that 10 dB is nothing but this, or log K is 10 by 20. That implies K is equal to, you have to take anti-log 10 to the power 0.5. 10 to the power 0.5. So 10 to the power 0.5, you will get it as, how much you'll get? K is equal to 3.166. So if you set the value of K as 3.166, the system will get a gain margin of 10 dB. More, yeah, that. Yeah. Okay. Yeah. You are able to hear. Very high. And when I checked, it was not working. So your voice is not audible. We are working on it. Just wanted to show you the progress. All right. I'll come back later. Okay, so that's how you deal with part 1. For a given gain margin, draw an horizontal line, and from omega PC, draw a line vertically upwards, such that it cuts your reference line, which is 10 dB line, and then measure the distance A dash B. So in order to get a gain margin of AB, what you have to do is you have to shift the magnitude plot by a distance of A dash B. So that should be done by incorporating K value. So you will equate 20 log K equal to that particular distance, which is 10 dB. And you take the anti-log and you will get 10 to the power 0.5, which you will get it as 3.166. So if you set K value as 3.166, you will get a gain margin of 10 decibels. So that's the first part. Now, in the second part, okay, you have been asked to find the value of K for a phase margin of 50 degrees. So what I will do, I'll erase this particular part. Okay. So this part is done. So I will cut it. Now I am left with 50%, 50 degree. Same approach. Locate 50 degree phase margin. Okay. So again, you have to look at the sign. It is plus 50 degree. So this is 30 degree. This is 60 degree. So somewhere here, right? So draw plus 50 degree reference line. Okay. Yeah. So this you can write 50 degree phase margin line. Okay. Now your phase margin is calculated at gain crossover frequency. So I think you have understood the procedure now. So you have to locate the phase crossover, the gain crossover frequency, and from that frequency you have to draw a straight line vertically downwards, right? So when you draw, what you get is you will get an intersection point somewhere over here, right? Somewhere over here. So this is point P, okay? So this point is P, this is Q, and this is R. So what is happening is, so you got it. Okay. So this, okay, fine. So this is R. Right. Now, again, getting 50 degree phase margin should be done or should be achieved by varying K. And the only possibility to get K is from the magnitude plot. So as I said in the beginning, draw a 50 degree phase margin line and locate the point R. So not here, because the line which cuts your phase plot will give point R somewhere over here. All right. So what you have to do is from that point, you draw a line vertically upwards. Okay, vertically upwards, such that that line cuts your magnitude plot. So the line will cut your magnitude plot somewhere over here. Right. Now let's say this point as point S. Okay. Now if you look at the magnitude plot, you would see that the intersection point with the magnitude plot is at S. But phase margin needs to be calculated at gain crossover frequency. So gain crossover frequency is the frequency at which your magnitude plot cuts 0 dB line. But your magnitude plot is not at 0 dB, right? It is at close to 10 dB, right, at this point. So what is that you should do? You are not getting 0 dB line, right? Instead, the magnitude is staying at non-0 dB, right? So you have to push your magnitude plot downwards so that this point S stays on 0 dB line. So you have to push down the magnitude plot such that the point S stays on this 0 dB line. So what you can do, PQRS. So this point on 0 dB line, you can take it as 2. So push down by length ST. Okay. So you will have to measure that length ST. So length ST, you will get it somewhere close to minus 14 dB. Okay. Now question is why minus? Because pushing down, right, is considered as negative. And moreover, this length ST is found above 0 dB line. So anything above 0 dB line is taken as negative value, and anything below 0 dB line is taken as positive. So this is minus 14 dB. You can find K by using the formula 20 log to the base 10 into K is equal to minus 14, or log K is equal to minus 14 by 20, or K is equal to 10 to the power minus 14 by 20. So 10 to the power minus 14 by it's not 14, it is 4 is. Okay, somewhere about 4 is. It's 4. So that will give you 0.6. Right. So that's how you calculate the value of K. Draw 50 degree line, and where it cuts the phase plot, that is at point R, draw a line vertically upwards, and that line will cut your magnitude plot at 2 distinct points, point S and point T. But to get phase margin, you should have gain crossover frequency. But gain crossover frequency is found at 0 dB line. But here it is not 0 dB. Hence, what you have to do, you have to push it down by a factor of length EST. So that corresponds to 4 dB, negative 4 dB. And that when you put it in your equation, you will get the K value as 0.6. So